Okay, so this title is slightly different than the title that is on the program, but it's the same subject. I'm not changing the subject. So this is numerical analysis for orbit propagation in Python. So the motivation for this talk is that basically we normally just use whatever is available on one of these commercial packages like SDK or MATLAB. So you normally just pick an integrator and use it for your specific problem. So in SDK we have like these integrators available. How many of you are familiar with SciPy and NumPy? So actually, many of you. So NumPy provides an n-dimensional array, which is like very similar to what we do in MATLAB. The only difference is that is zero-based index is the one. That's the only difference. And actually, SciPy implements a lot of different scientific and engineering tools that we can use. And SciPy is open source and is free, as previously was mentioned. And those are the integrators, like some of the integrators that are available for SciPy, and are the ones that we use for initial value problems. But even if we know these integrators and we have what input parameters and output parameters we should use, the thing is that we as programmers should be aware of how the specific integrator is going to perform and how stable it's going to be with our specific problem and with our specific initial conditions, with our perturbations for eccentric orbits, and like very importantly is how these integrators are going to perform with large time steps when we want to run like long run simulations. So that's like very important. If you take a look at SciPy code, you actually see that these integrators are not implemented in Python. They are implemented on Fortran, and NumPy provides an interface to Fortran, to C, to C++. So you see the code of the integrator. It's very long. So you can do the same thing using Python, but using NumPy and like ND arrays structures to hold all your data, and it's like a much shorter program. So the purpose of using Python here is just to do the numerical analysis, since most of these algorithms are not like suitable for parallelization. So we don't really like get any advantage of using a multi-core architecture. How many of you have heard about the global interpreted lock in Python? So that's like the most infamous thing that Python has that prevents you to like run more than one thread at the same time. So if your algorithm is suitable for parallelization, so you shouldn't implement it on Python, but these things are like iterative, so we're good with Python, at least for analysis. So I divided this talk in three parts. The first part, we're going just to have a primer of the initial value problems we're going to handle here. The second part is going to be like specifically like error analysis for these numerical methods, and the last part is going to be how consistent and how convergent and how stable are our algorithms for our specific problem. So this is like the most general form of our initial value problem. We have our state vector here. We have our like vector valued function at the right hand side, and we have our initial conditions. So if we want to write our embodied problem ODE in the form that we saw in the previous slide, so we have a second order ODE here that we want to rewrite as a system of a couple first order equations. So we just write it like our state vector is going to be my position vector, my velocity vector, and in the right hand side I have this evaluation of the function that we saw at the top of the screen. So this is the problem that we want to solve, this coupled system of first order ODEs. As you can see, this is like very non-linear because of the dependency with R to 3. So not all integrators are good for this kind of problems. There are integrators that are very good for linear problems, but for nonlinear problems, some of them have some issues. So this is like a very rough code of how we implemented the right-hand side of our system of first order ODEs. So we have here like our input parameters. Like we know that this right-hand side function is autonomous because there's no explicit dependence of time t. But for the sake of like readability, we put here the t, which is like the time step at which I want to evaluate my right-hand side function. And I have like this gravitational parameter defaulted to Earth. So what are we going to return is I'm going to advance one step in time my state vector, which is u, like represented in an ND array. So this is like extremely simple. It's just like dr is going to be v and dv is going to be this other expression. I am using from NumPy, I'm using the norm. This norm, we know that in finite dimensional spaces, all norms are equivalent. So this is defaulted to the 2 norm, so that's just fine. And then I'm going to use slices to assign to my first 3 positions what I found for dr, and then for dv, and just return another NumPy ND array. So I'm going to go through this a little bit quicker than expected, but what we want to, for our right-hand side, to ensure uniqueness and existence. So we need to know, is our right-hand side continuous to ensure existence, and it's continuous differentiable to ensure uniqueness? So we want to answer those 2 questions, and what we want to ensure about our specific problem is that this problem satisfy the Lipschitz condition, which is like given my domain, I want to ensure that this is Lipschitz continuous on u at least up to some time t. So we are not going to simulate this up to infinity time, but we want to maximize the time up to our simulation is going to be run. I want a long run simulation, but I want also like a large time step. So let's say this is our domain, and the Lipschitz condition is that there exists this constant L greater than 0, such that this condition holds. What does it mean is that our right-hand side function is not too wild, that for every small change that I do on u here, is not going to result in something like very wild and very big. Is it this true for our right-hand side, for our like 2-body problem? It's true there, as we're going to see, but we know that near the periapse, our velocity vector changes like very dramatically in direction and magnitude. So it can be wild under some conditions, and since our dependence on the denominator on R, our domain has to exclude R equals 0 to be continuously differentiable. So if our right-hand side is like all the partial derivatives are bounded, so I can find my Lipschitz constant to be like the maximum of all my partial derivatives. So to answer the question, is our right-hand side Lipschitz continuous? It could be, and it can be shown that if my function is like a mapping from Rn to Rn, in this case n is going to be 6, because we have 3 components for each vector. So it can be shown that it satisfies the Lipschitz continuity with this Lipschitz constants. So it's Lipschitz almost everywhere, excluding r equals 0. This is going to be useful for determining up to what time we are able to simulate before blowing up our simulation. Okay, this is the second part. It's about like a specific like numerical method that we want to use. These are like the most basic schemas: forward Euler, backward Euler, leapfrog, which is like very, very unstable, and trapezoidal, which is very stable, but it's inaccurate. So we need to start like seeing the trade-offs we need to make between accuracy and stability. So we're going to go over the Runge-Kutta family that are methods that are one-step and multi-stage, because it's not multi-step because I am using only the current evaluation of my state vector. And what we do is just to compute intermediate stages at different times, and then we basically just do a linear combination of these results. So we need to, there are ways to calculate the coefficients of this linear combination depending on the order of accuracy that I want to achieve. The number of stages is not the same as the order of accuracy. So if I have a Runge-Kutta, this is only true for S less or equal than 4. So up to 4 stages, the order of accuracy and the number of stages is the same. But if I want a Runge-Kutta solver that is 5 order accurate, I need more than 5 stages. So this is an example for Runge-Kutta 2. Again, this is like a very simple implementation of the Runge-Kutta 2 stages. So basically, I get a time vector, which is again an ND array. I get my initial conditions, my right-hand side functions, because this I should be able to evaluate this same function for different problems. And I set up my initial conditions, and I just start iterating through the different time steps. In this case, in Python, there's nothing we can really improve here, because first, I cannot parallelize this, and second, even if I could, I can't in Python because of the global interpreted log. This is the coefficient, like the 4 stages and the coefficients of the linear combination for Runge-Kutta 4. This is again the implementation, so we can hear that the y's here are our stages. Yes, the intermediate stages. What we see here is that while we are getting more accuracy with 4-order accurate method, we are doing much more evaluations of my right-hand side function. I am doing here like 4 evaluations. So if I have a function that is expensive to calculate, I am going to get like more accuracy at the expense of like more computation time. There is this other method that I really like, that is the implicit Runge-Kutta. There is this quote that it's funny because it's like the Gauss-Legendre methods are the Lamborghinis of numerical ODE world. They are expensive and hard to drive, but they have a style. The thing is that these ones are you can get like the best accuracy with this type of methods, but we need to do many evaluations of my right-hand side. So that is expensive as the Lamborghinis, but they really give me like very, very good stability and accuracy. So this is an example for a 2-stage Runge-Kutta implicit using the Gauss-Legendre quadrature formula for integration. So the coefficients that we see here, like the Ci's, are the series of the Legendre polynomial that of order of degree 2 that we see here. The Ij's are also related with the quadrature formula, as well as the Bj's. So these implicit methods are like, when you have this method that is implicit, so you need to calculate your future because you don't really have the future value. So the other problem is that we need to use an iterative method to solve the nonlinear system in every time step. So as we, is it very small? Yes. So the thing is that we need to solve in every time step. We need to use an iterator like the Newton-Raphson, and as we see here on the last 10 lines, because I need to do an estimation of what my future value is going to be, and then I use that value for the final calculation. So until this iterator converges, I am going to perform like many more evaluations of my right-hand side function. So this is why this is really expensive, but it's we are going to compare the order of accuracy of this and the stability later. So the linear multi-step methods are, this is like the general form. These ones, unlike the previous one, this uses like multiple evaluations of my state vector. So if R here is representing the number of steps I am using, so if the BR's coefficient is 0, then my method is explicit. In practice, we always use the alpha R equals to 1. So this is like the family of Adams methods, where we choose alpha R to be 1, alpha R minus 1, minus 1. The rest of them are 0. So depending on my BR on the other side, my methods are going to be implicit or explicit. So we have the Adams-Bashford method, which is an explicit method, and then my BR is going to be 0, but then I want to pick up the BJs to eliminate as many terms as possible from truncation error that we're going to see later. What is this? The problem with these methods is that requires bootstrapping. That means that I need to use another method to calculate my first evaluations of my function. So in the case of 2-step or 4-step Adams-Bashford, I need another method like Runge-Kutta to evaluate 1 n plus 3, 1 n plus 1, or 1 n plus 2. And so this is the Adams-Bashford. Then I have the Adams-Moulton, which is the implicit method. And it's only 1 order of accuracy greater than the explicit version. So that's not great, because for the implicit Runge-Kutta, I can get 2 times the number of stages. For this one, I get the same, the number of steps is my order of accuracy. With this implicit, I'm just getting 1 more, so it's not great. So this is how we could implement an Adams-Bashford-Moulton, which is the predictor corrector. So if I don't want to use an iterator like the Newton-Raphson iterator to evaluate UN plus 2 in this case, so what I can do is like use an explicit method to estimate in this case, UN plus 2. And I can use Adams-Bashford to do this. So that's like called the prediction. And then I can use Adams-Moulton to do the correction over that estimated value. So this is what we're doing here. Still, I am bootstrapping my method using Runge-Kutta. Then for each time step, I am predicting with Bashford, and then I am correcting with Moulton. So I ended up using 3 methods here, and all for getting just 1 order of accuracy more. So, well, it's not great. For error analysis, then what is like just the truncation error is like the result of neglecting higher order terms in my approximation. So you get this like replacing in your expression for your method, you replace the Taylor series expansion of your true solution, and then we start like canceling out terms with your method. And then we get the truncation error. It's just replacing the true solution into the method. So this method is consistent. Like if delta t goes to 0, my truncation error should go to 0. So what we're going to do here for our modeling the order of accuracy or comparing the order of accuracy is that we are going to model my error depending on the delta t I choose, and it's going to be like a constant multiplied by some like delta t to the power of my p, which is the order of accuracy. So as I mentioned before, I am just replacing the Taylor series expansions into my expressions for each of these basic methods, and this is what we get. For Runge-Kutta 2, we get that some of these terms start canceling out, and I get this, that my error goes as the square of my time step. This is the truncation error for linear multi-step methods like the Adams family. So there is an error here. This P should be for like all, if I don't have, yeah, there is an error here. It should be, all P's should be greater than 0. So if I have terms that have a 0 power of P, these terms should cancel out for the method to be consistent. So the condition for the linear multi-step method to be consistent is that these sums here, like all the sums of all my alpha j's should be 0, and this other condition here should be satisfied. So how are we going to visualize in Python the order of accuracy for our specific problem? So we're going just to model how we expect the error to behave. So we find this constant C that we saw here. We're going to model that as a lambda function in Python that I am going to pass as parameters my time step, my error, like my initial error, the error I get in the first step, and the order of my method. So I'm going to use my right-hand side for the two-body problem. I have some initial conditions for some satellite orbiting Earth, and I'm going to simulate for 1 day. I'm going to start comparing like from a coarser to a finer grid. So from 600 time points to 36,000, and I am going to get, this is like just like some parts of the program, but I'm going to start comparing the solution vector that that the method gave me against the true solution, which we computed analytically using Keplerian elements and everything. That's my true solution. And then I'm going to plot my expected order of accuracy and my actual error that we get. So in this chart, what we see is that for Runge-Kutta 2, it's indeed second order accurate method. So we see that when our delta t is in the order of 10 to the 2, when I reduce this to in one order of magnitude to 10 to the 1, then I kind of reduced my error on the square of my delta t. For Runge-Kutta 4, this is fourth order accurate, but this implicit Runge-Kutta that we plotted here in green is fourth order accurate, but just implementing 2 stages. So this might be the same. Runge-Kutta 4 and implicit Runge-Kutta might be the same for smaller and smaller time steps, but what we want here is larger time steps because we want to run the simulation for a long time. This is, I'm going to compare now the errors between Runge-Kutta 4. I am like, if you can see the last parameter here is 455 because I expect this Adams, Bashford, and my predictor corrector to be 5th order. So what I get here is, yes, they are 5th order compared to my Runge-Kutta and Adams, Bashford, but the predictor corrector is just like too complex to implement, and it requires bootstrapping, and it's 3 methods in one, so it's not really worth to work this for our problem. So I'm going to go a little bit faster on this last part, which is about convergence. So what we want is that at the final step of my simulation, as my delta t goes to 0, I want to converge to the true solution. So for a method to be convergent, I want to satisfy 2 conditions. The consistency condition, which is that my truncation errors should depend as of the power p of my, okay, there's a delta t here, it's not just delta. And this p should be bigger than 0. That makes the method consistent. And it should be 0 stable. This is like an extra stability condition. It's like a relaxed stability condition. That means that the sum of total errors as delta t goes to 0 should be bounded and should be the same order as my truncation error. This is like a general convergence for one-step method. But the interesting part is here about the 0 stability for linear multi-step. So what I want to, for 0 stability means that I want to find the zeros of my characteristic polynomial, which is like using my method to solve the trivial equation, the trivial ODE, and then I get the roots for this. So the condition is that all of them must be less or equal than 1, and for the ones that are, they shouldn't be repeated, but for the ones that are repeated, they should be strict. There's an error here. It should be strictly less than 1. So for Adams methods, after we find the zeros of our characteristic polynomial, we find that there is one root that is equal to 1, and the rest of them is 0. So all Adams methods are 0 convergent. They are consistent because of our specific selection of coefficients. So all Adams methods are convergent. So for stability regions, we want to do this analysis to know if our method is going to blow up at some point. So we have that for stiff problems like our problem, the more accurate we get, the smaller my stability region is. So my stability region is basically where my eigenvalues of my problem should be. So if I have large eigenvalues, I want a big stability region so my problem, my solution doesn't blow up. So for our system, which is a nonlinear system, what we can do is like finding the eigenvalues for this, which ends up like we can find like 5 eigenvalues from here. So what we want is that we want these eigenvalues to be in the absolute stability region, which is like the shaded area. So if there is, this is the stability region for backward Euler. So if all my eigenvalues in general for this problem are going to be real numbers, negative, so I want all of them lying on the real line, but outside this white circle. If some of them lies in this, and that can depend on the initial conditions, so my solution is not going to be stable. So I didn't plot here, but for example, this is a very good stability region, but if I start like increasing for an implicit method, I start increasing my order of accuracy, this white circle here is going to start getting bigger and bigger, so it's the trade-off we have to make. So this is like what an unstable method do. For example, the one in blue is the Runge-Kutta 4 when I am using a fairly, okay, I'm going to finish very soon. the the fairly larger time step, so it's like it blows up after some point, but you can see that implicit Runge-Kutta, it might be not very accurate, but it doesn't blow up. For like smaller time step, they do like fairly similar. So the conclusions is that both the implicit Runge-Kutta and Runge-Kutta-4 methods are very good in terms of accuracy, but the Gauss-Legendre method proved to be like much more stable because implicit methods are. But however, it's a little bit more complicated to program because this is going to carry like many extra evaluations of my right-hand side. So again, we need to find a balance between accuracy, stability, and computational resources. Like for, in this case, the linear multi-step methods, we demonstrated that those are like consistent and convergent, but it can be unstable for some problems that are very stiff. So we just forget about linear multi-step methods for orbit propagation. And regarding Python, we know that NumPy is not written in Python. NumPy is written in C. So, but still Fortran arrays are like performs much better than the NumPy array, but they are a huge community still working on this. It's a very active community. So the idea is like to get the same performance as Fortran in this case, but we can achieve like the same results of Fortran in fewer lines of code. In the future, we might explore Julia. That is a language that it's a new language for scientific computing that might be interesting, or we can just switch to the PyPy implementation of NumPy, which is NumPy. Like most of the NumPy functionality has been already ported, and PyPy is a JIT compiler, is not interpreted as Python, so it might be an option. So that's all. Thank you very much. If you have questions.
Hi, this is a little out of my field, so I apologize if this is a silly question. But did you implement this in Python and then pick a spacecraft in Earth orbit and compare your results either to STK output or to the ephemeris NORAD provides? And if so, how accurate was your approach?
It's the problem with implementing this in Python is not actually accuracy, but is that is very slow. So if I start running this and I want a fairly small time step and I want to run this for days and days and days, it's going to take forever. That's the problem. But accuracy is very comparable to what we get on SDK.
Okay. So are you saying that it's not a practical approach for someone flying a spacecraft and needs timely orbit information?
Yeah, it's just useful in this case for doing analysis. But as I mentioned at the end, this could be, it could be an option to implement this in the PyPy version of NumPy, because that's very comparable to what we can get with Fortran, and most of the functionality has been already ported. So